Hello, everybody. My name is Gitanjali Sethi, and I am an Associate Professor of Physics at St. Stephen's College, University of Delhi. I have more than 20 years of undergraduate teaching experience. I did my bachelor's and master's in physics from St. Stephen's College and my PhD in theoretical cosmology from Department of Physics and Astrophysics, University of Delhi, under the supervision of Professor Daksh Loya and Professor Amitabh Mukherjee. And for my undergraduate teaching, I have taught almost all papers in Delhi University curriculum. I have always believed in updating my teaching with current research in respective areas. I have always adapted to new teaching and assessment methods in my classroom teaching. I try to integrate modern research in my classroom teaching through my tutorials, assignments, and projects. I have also handled almost all laboratory courses associated with undergraduate teaching in University of Delhi. I have modified my labs using latest data acquisition tools like Arduino and other online softwares. I have prepared online lessons in mechanics for University of Delhi undergraduate teaching. I have also given lectures on fluid dynamics for National Academy of Sciences Delhi chapter. This was during COVID to help students prepare for their examination. I am also a lifetime member of IAPT, IAGRG, and an associate of IUCA. I have been encouraging my undergraduate students to participate in various activities of these associations, and I have mentored them through these activities. I have also encouraged my students to participate in various national and international competitions, and I have mentored them through these various competitions. Like there has been an antenna design competition being organized by IUCA for last few years, and I have mentored my students for that. I have also mentored my students for an international physics problem solving competition in the year 2020. I have also mentored international students at high school and undergraduate level through New York Academy of Sciences and Supernova Foundation. I was the staff advisor for Physics Society in college for 6 years. Through this society, I have organized various physics and science related activities in college. In addition to my teaching responsibility, I also have administrative responsibilities. Like currently, I am the director of St. Stephen's Center for Advanced Learning. The aim of this center is to organize professional courses for national and international participants. For my research, my current area of research is data analysis in astronomy and cosmology. Currently, I am working on a project with a faculty from RRI on pulsar data analysis. I am also working on a project involving building an affordable radio telescope with my undergraduate students in college. This will provide them with the tool to do research in radio astronomy. Most of my current projects involve my undergraduate students. For example, the radio telescope project involves three undergraduate students from my physics department. There's another currently running project on characterization of exoplanet atmospheres. This involves three physics and two chemistry students from college. I have also mentored undergraduate and master's level students through a STEM based organization called SASTEM. Recently, with a group of students through SASTEM, we published a paper on gravitational wave data analysis in an international peer reviewed journal, Astrophysics and Space Science. I have also submitted another paper on structural colors with undergraduate students from the chemistry department to Brazilian Archives of Biology and Technology. And I have also worked towards popularizing and promoting science at high school level through a research organization, SASTEM, through a research organization, Research Discovery. Recently, one of my papers with a high school student through Research Discovery on characterization of exoplanets was published in Journal of Emergent Investigators. I also coordinated a 30-hour long Python workshop in college for the students. In past, I have published work with undergraduate students from college and outside college also. My past research expertise has been computational and theoretical cosmology. I have successfully undertaken various funded projects at undergraduate level. I have successfully completed two 5 lakh rupees projects funded by the University of Delhi under the Innovation Scheme. Both these projects were interdisciplinary. One was with the chemistry department titled Molecular Design, Synthesis, Characterization and Application of Macrocyclic Compounds. Similarly, one was with computer science department on computational methods in statistical analysis in astrophysics. Both these projects involved undergraduate students. I recently completed another 3 lakh rupee project funded by the University of Delhi under the Institute of Eminence FRP scheme titled Constructing a Radio Antenna for Observing the Universe. Till date, I have around 7 publications in international journals of high impact factor, including Physics Letters B and IJMPD. In last 4 years, I have contributed 4 posters and 4 talks in national and international conferences. These include a talk on affordable astronomy in college at an international conference, GAU, in August 2022, and also a talk in the national conference ACFP 2023, where my abstract was also published in the conference proceedings. My publications also include essay metrication of Berkeley Physics Volume 2, Electricity and Magnetism through Tata McGraw-Hill, and I have edited chapters of a book by Cambridge University publication. I may or may not be able to compile all my achievements in last 5 years through this video, but I feel that my biggest achievement is to be able to apply for this reward. Thank you. Is a direct. I can always give some charge to this conductor, right? So when I give some, let's say I give some positive charge to this conductor. This is what I call as free. Why? Because this is under my control. But moment I do this, there is a dielectric. What will the dielectric do? What would be the effect? There is going to be an induced. Because this is like placing dielectric in an, there is a, I mean if you don't imagine, if you imagine that dielectric was not there, this outer ring was not there, there is going to be electric field due to this free charge that exists on your spherical shell. Yes or no? Right? Do you agree? So this is a situation where my system itself has both free charge and bound charge. So that's what I call as free charge. Right? Free charge is something that's under my control. So I'm looking at a situation where I have done this some time back and it has reached some stable configuration so that now I have electric field E that I see in my system. Now this electric field, we obey Gauss's law. Okay. We go back. It's an electrostatic field. If you remember, what was Gauss's law? Gauss's law, you can see it in integral form, differential form. It's nothing but when looking at Coulomb's law in situations where systems have some kind of symmetry, is that you can use Gauss's law to find electric. So there is nothing special. Right? I told you, every electrostatic field will always something, it will always obey. So from Gauss's law, in differential form, I have del dot E equal to rho by epsilon. Now the electric field that I am talking about, as I told you, is the field which is net effect of both bound charge and free charge. So what is this right hand side? This right hand side is then rho b plus rho f by. Are you happy with this? Does everybody agree? That's the property of it. That's what I've seen. Every electrostatic field can always be written down. Its divergence is always equal to the volume charge density divided by epsilon. So I have rho bound plus rho free equal to upon epsilon naught. So let me rewrite it here. But then, if you remember when we were talking about physical interpretation of bound volume charge density and bound surface charge density, in the last class we saw that I can write rho b is nothing but minus del dot P, where P is my polarization vector, dipole moment per unit volume. I substitute it here. But before I substitute it, I just take the epsilon naught on the other side. So now my equation reads del dot epsilon naught times E equal to minus del dot P plus rho. I've just substituted for rho. So what you see now on the right hand side is only free charge volume density, right? This quantity, this vector D is what I denoted with, which is equal to epsilon naught E plus P, is what we call as the displacement vector. It's a very important quantity, we will see, we will realize it's extremely important. The left hand side is taken care of the induced effect, right? If you look at epsilon naught E plus P, has taken care of the induced effect in such a way that now this D only depends upon what? It only depends upon my the free charge density, right? It only depends upon, this is like Gauss's law, right? So if I have a dielectric material, in case of dielectric materials, in presence of external electric field, the net electric field E and polarization P, this vector D satisfies Gauss's law as del dot D equal to rho. This only depends upon, the important thing about D is that it only depends upon rho F, right? Now, one very important immediate use of defining this vector, I can tell you. If I to draw another figure, look at this situation itself. Right? As I go from inside to outside, right? When I look at this region within the dielectric, or so let's mark it. Let's say the inner conducting shell has a radius A, and this is B. Right? If I look at region A to B, in region A to B, you have both free charge and bound charge. If you look at electric field, it depends upon both bound charge and free charge. So you will have some value of electric field here. When you will go out, this is a conductor. This is vacuum now, right? There is no bound charge here. You will see, as one can reason out from here itself, bound charge exists only inside the bulk of the material, in the bulk of the dielectric, that is between radius A to B. Right? There is no volume, there is no bulk, there is no bound rho B in this region. Rho B exists only in the region between A to B. Right? So this right hand side has rho B and rho F. So there is going to be some electric field here, which is definitely going to be different from what is beyond B. Why? Because beyond B, there is no rho B. There is no rho B. Rho B only exists within the dielectric. Whereas, so you will see that electric field will differ when I look at it inside the dielectric here in this particular problem. We will solve this problem soon. Electric field is different in the region A to B, and it is different in the region beyond B. Whereas, if you look at the displacement vector only depends upon free charge, right? The situation doesn't change when you go from bulk of this dielectric to the region beyond, right? Because the free charge density remains the same, and we will see as a result when we will solve this problem that D is going to remain same when I go from the region starting A to B and beyond B. Right? So this is going to be a very useful quantity. Right? Let's do one numerical problem to see what is the role played by this D in my, how do I calculate D using Gauss's law. And then there's a warning that I'm going to give you, which is going to be extremely important. Is this clear to you till this point? Let's do a very simple problem based on what we've studied. So let's say I have a line charge. So you can note down the problem maybe. You have a straight wire, a long straight wire carrying uniform line charge lambda. It is surrounded by a rubber insulation. So rubber is a dielectric. It is surrounded by a rubber insulation up to some distance r. So it's like a wire and then a cylinder. Right? This is something that you see in your daily life. When you work in your lab, you have a conducting wire carrying some current. In that situation you have current, and then you have a rubber insulation out to a radius r. I want you to find D in two very clear demarcations, two regions, between 0 to capital R and in the region beyond that. In the region beyond. Let me do this problem for you, then you do the next problem for me. Now this problem has a cylindrical symmetry. Let's apply Gauss's law. You know that if I want to apply Gauss's law to find D, this is how I do it. What should be my choice of Gaussian surface? So first let's solve for a region R less than the extent of my rubber insulation. What kind of a Gaussian surface do you think I should choose in this case? Cylinder, right? Because my problem has a cylindrical symmetry. The natural choice of Gaussian surface is a cylinder. I just want to ensure. Right? So I look at, for R less than R, I consider a Gaussian surface which is a cylinder of this radius R. Right? Now I have written it down here, this equation in differential form. I can write it in integral form just the same way we did it for electric field, and that would imply that D dot ds should be equal to total free charge enclosed. What is important to note is, one, it's only free charge enclosed. Second, there's no epsilon naught. Right? There's a difference of epsilon naught, and that's an important thing. It's not just a mathematical fact that epsilon naught is not there. Right? It's in fact, because epsilon naught is not there, is that you see it is continuous over the boundary of vacuum and dielectric, as we discussed in this case. Right? It's important. Mathematically you see it's not there, but there's a very important fact behind that mathematical statement, that there's no epsilon naught. Right? So let's use it in this form. If I use it in this form, what would be my left hand side for this Gaussian cylinder? It will be just now, because it's a line charge, right? And the way you define D, if E is in radial direction away from the axis of the cylinder, so would be your D. So if I look at D dot ds, D is along the radial direction, that is the radial vector pointing away from the axis of my cylinder. So left hand side I can very easily hence write it as D times what would be my left hand side? 2 pi r. 2 pi r times L, where L is this length of my Gaussian cylinder. That's my left hand side. Right? 2 pi rn is this curved surface area. Because it's a curved surface area on the surface of the cylinder, the surface element will also have direction along the radial vector. So that's why D dot ds is simply D times ds. I can pull out D from the integral and I get 2 pi r. Is everybody comfortable with this? Right. Now the right hand side. What is free charge enclosed in this Gaussian surface? Lambda times? Yeah. Because the free charge is only the line charge density. Right? The free charge is only the line charge density. There is going to be an induced charge in my rubber insulation, right? But D doesn't depend on that. First, do you agree there is going to be an induced charge? Are you convinced? Yeah, because we've seen that. That's what happens. It doesn't change. The facts don't change if I start doing a problem and I leave the theory. Right? We just studied. What did we study? We studied that whenever I have an external electric field, this line charge is a source of external electric field, and I have a dielectric material. Wherever it is, surrounding, away, right? It will experience the external electric field. And how will it respond to it? And that's what this polarization P is a measure of. Right? Okay. So what do I get my D as? Lambda by 2 pi r. And what would be its direction? We've just seen. Lambda by 2 pi r, r cap. Right? We've seen this. Yes or no? Is everybody with me? Do you follow this point? Good. Now if I look at the region r beyond r, how will I do the problem beyond r? I'll use the same thing, right? I'll still use Gauss's law in integral form. So I still have to find D, right? Again, what would be my choice of Gaussian surface? It will still be a cylinder, right? This time it's going to be a cylinder. If let's say here is the point P where I am finding it, and this distance is now my R, is I consider a Gaussian cylinder here. What would be my left hand side in this case? Again, I choose the length to be Gaussian cylinder to be some L only. What would be my left hand side? It's going to be the same. Is everybody with me? Yeah. So left hand side is D times. What about the right hand side? What about the right hand side? Yes, it has to remain same. Why? Because it only depends upon free charge. So what do I have on the right hand side? What I have on the right hand side is again lambda times L. And you see what I just told you. D is lambda by 2 pi r cap. Exactly the same that I got in case of, that's because it only depends upon free charge. You see the importance of this vector, displacement vector? It's continuous over the boundary. Right? So the left hand side here in this equation has so got adjusted that the right hand side and hence this vector D only depends upon free charge. Right? Now, can I find E in this problem? Can I find E in this problem? Yes? How will I find E in the first case where I have small r less than capital? You need to tell me. It would depend upon both bound charge and, do I know the bound charge? Do I know the bound charge density? You have to be confident in yourself. You need to tell me, do I know the bound charge density? Can I find the bound charge density? What do I need to find the bound charge density? Do I know polarization? Yes? Who says yes? If yes, tell me what it is. I don't know. I have no idea about polarization inside this diagram. Right? I cannot find polarization. It's like, to find polarization, I need to know the bound charge. Or to find the bound charge, I need to know the polarization. I don't know either. I cannot find P unless I have some more information, as we will see in some later talk. Right? Unless there is a way of finding, I know a scheme to find P, I cannot find P in most general cases. Do you agree? Yes or no? Right. If you agree with that, greetings.